On December 7, 1941, Shigenori Nishikaichi's Mitsubishi A6M2 Type 0 Model 21 aircraft tail code B11-120 was damaged during the return from Oahu, began losing fuel, and could no longer complete its planned return vector to the carrier Hiryu. The pilot was forced to divert west, executing an emergency landing in a dirt field on the privately owned Hawaiian island of Niihau, where the isolated site remained outside the primary wartime theater until a dedicated team from the Pacific Aviation Museum initiated a formal archaeological recovery nearly 65 years later. The institutional objective was rigid. The team was tasked to locate, extract, and forensically identify the highly degraded fragments of the historically significant airframe. The operational constraint was extreme exposure. After 65 years open to the elements, the wreckage was no longer an intact aircraft. The transition from a functional military machine to a deteriorated artifact fundamentally dictated the recovery methodology. A standard bulk salvage operation would have simply scooped up the remaining metal, destroying all forensic value. Instead, the museum treated the site as an archaeological recovery. The process prioritized pre-disturbance documentation over rapid extraction, preserving the remaining fragments in record before any movement altered their context. Terrestrial open terrain recovery presents a distinct forensic problem compared to underwater operations. In deep water, extreme depth limits human interaction and locks the site in a relatively stable mechanical state. On land, the wreckage remains continuously accessible to oxygen, weather, and physical interference. That exposure left the recovery team working inside a severely weathered footprint. Aluminum alloy had oxidized under alternating moisture and heat, and the dirt field and heavy brush of Niihau had consumed many of the lighter structural elements. The authorization granted to the team required careful adherence to preservation standards. To achieve a defensible identification, the team required more than a pile of corroded metal. The anchor evidence came from the known tail code B11-120, surviving portions of the airframe, historical photographs, aircraft drawings, and comparison with another A6M2. Without those cross-checks, the identity of each fragment would remain uncertain even if the aircraft's overall history was known. The recovery team drafted a careful extraction plan because the relationships between the pieces, as they were found in 2006, had to survive the translation from the dirt field to a controlled museum space. This approach meant treating every surviving scrap of metal as a specific node in a larger engineering problem. The eventual goal was to transport the components by sea to Oahu for a disciplined floor grid reconstruction. The team planned to utilize relative part spacing on the grid to deduce structural relationships for unrecognizable fragments. Every decision made in the brush was governed by this future requirement. They needed to secure the site, stabilize the heavily oxidized structures, and prepare the pieces for transit without inflicting further mechanical stress. What had to be preserved was the as-found orientation of the remaining fragments in the secondary site, not a clean map of the original impact geometry. The immediate physical state of the wreckage presented a sharper problem than ordinary weathering could explain. A forced landing typically leaves a recognizable fuselage, wings, and a coherent empennage. But the team faced isolated structural sections, a heavily damaged engine block, and scattered debris with no continuous load path. With the site exposed for 6 decades, what mechanical forces and human interventions had reduced the intact airframe to scattered fragments? The requirement to eliminate sensitive military material created a stark trade-off between operational security and structural integrity. The aircraft was damaged by the forced landing, but the primary destruction did not come from crash kinematics. The landing structure initially remained largely intact, with the load paths from the engine to the tail still mechanically connected. However, the operational security mandate forced a radical alteration of the site. Late on December 12, 1941, Nishikaichi returned to the aircraft with Harada and a captive, attempted to use the radio, removed the 2 7.7mm guns from the upper cowling, and then set fire to the cockpit area. This was an explicit tactical decision to deny useful equipment and information to the Allies. The airframe became the fuel for its own destruction, shifting the site from a localized mechanical failure to a catastrophic thermal perimeter. The burn event stayed localized but severe. It damaged the cockpit area, the structure beneath it, and the main spar region, destroying instruments and weakening the central airframe while leaving the engine, wings, and portions of the tail within the evidence record. The extreme temperatures established a permanent forensic constraint on the material, but the damage perimeter still had to remain narrow enough to match the surviving evidence. Later inspection and salvage then removed additional material from the already burned wreck, blurring the original impact physics with fire damage, cutting, and decades of exposure. The site was no longer a simple forced landing scene. It had become a damaged, disturbed, and weathered wartime artifact. Before the site was left entirely to the open terrestrial environment, it experienced a secondary phase of rapid evidence reduction. Initial 1941 military operations at the site were defined strictly as immediate military intelligence salvage. The extraction personnel arrived under strict orders to secure specific technological assets rather than document an intact aircraft. Intelligence salvage is the rapid wartime extraction of critical items which fundamentally alters the remaining mass and heavily limits any future forensic baselines. The sole priority was hardware exploitation and technological evaluation. The military units did not treat the field as an archaeological scene, and they implemented no spatial mapping protocols for the overall airframe structure. The immediate wartime alteration of the aircraft unfolded in more than one phase. Nishikaichi and Harada had already removed the two 7.7mm guns before the cockpit fire. U.S. personnel who reached the site days later then inspected the wreck as a captured enemy aircraft, cutting and removing selected components and, in some cases, taking pieces as souvenirs. The propeller and hub, the tail light, and other small pieces later appeared outside the main wreckage record. The original spatial geometry of the engine mounts, weapon positions, and forward bulkheads was not preserved as an archaeological scene before those removals. After the specific military and curiosity value had passed, the remaining burned aluminum was left to the island environment. Together, thermal destruction and mechanical stripping erased the future baseline. The main body lost structural continuity, the forward sections lost durable identifying components, and the field was left with a highly distorted footprint. The remaining lightweight metal framework was severely compromised, lacking any remaining structural integrity to resist future physical displacement. When the 2006 recovery team finally reached the brush, that distortion raised a more specific question about whether the debris field had been displaced after the aircraft was first inspected. The physical evidence on the ground presented a difficult contradiction. One later account states that after inspection, what remained was dragged roughly 300 yards beneath trees to conceal the captured aircraft from possible Japanese reconnaissance, while another wreck record describes the remains as staying in situ where it force landed. Either way, the debris pattern could not be treated as an untouched mechanical print of the landing sequence. This uncertainty introduced the forensic constraint of possible secondary displacement. When wreckage is moved or cut before formal mapping, part spacing loses value as evidence of crash kinematics, impact energy, structural shedding, and impact angle. Measuring the distance between a surviving wing spar and a burned engine section could still document the 2006 condition, but not the aircraft's behavior during the forced landing. Facing a site with compromised original context, the team had to establish a stable spatial baseline of the current condition before initiating physical extraction. The team therefore enforced pre-disturbance guidelines, photographing and cataloging the fragments as they lay before handling, locking the localized context that still survived. Even adjusting a degraded panel to search for a mark or tag risked damaging the last available layer of field evidence. To execute this requirement, the recovery personnel prepared a photo mosaic of the wreck. The dense vegetation and terrestrial dirt of Niihau complicated the visual survey, so the team documented the wreck at close range before moving the larger pieces. The mosaic recorded the orientation, overlap, and exposure of the visible fragments as they were found. It did not reconstruct a full chronology of how the site had changed over 6 decades. It preserved the 2006 condition as a practical reference for later identification. By locking down the precise coordinates of the secondary footprint, the team ensured that no fragment could be orphaned from its field location during the lift. Photographing the degraded scrap in the brush secured the modern spatial baseline, but interpreting what those scraps originally were required a mathematical link to 1941. We can verify the precise dimensions of every fragment extracted from the Hawaiian dirt, but the recovered mass represents only a fraction of the historical airframe. The visible metal can be stabilized and secured, but the missing structure creates a severe procedural limitation. It was initially unknown which missing bulkheads were destroyed by the intense heat and which were stripped away by unrecorded human scavenging over the decades. To isolate the original loss sequence from subsequent contamination, the investigators had to establish a rigid boundary between thermal damage and civilian looting. Before answering that historical question, the physical evidence had to be removed from the brush under a strict identification system. As the team lifted degraded panels and fractured spars from the dirt, the larger pieces were tagged so each could be linked back to the photomosaic recorded during the initial survey. The physical lift was executed carefully by hand to reduce the risk that oxidized and brittle aluminum would fracture further. The tagged debris was then moved from Niihau to the controlled museum environment on Oahu. Once the material was unpacked, the analysts moved from field control to loss analysis. Because the causes of loss could not be separated mathematically, the team used those controls to test what the recovered material could still support. The team then turned to historical photographs made by Reverend Paul Denise during the wartime inspection. Later accounts describe the collection differently, with one account saying more than 500 photographs and another saying more than 400, but both point to a large visual record made close to the original event. The images gave investigators multiple wartime views of the burned and disturbed sections, allowing modern fragments to be tested against the aircraft's documented condition close to the original event. They systematically compared the newly tagged physical fragments on Oahu against those reference controls, looking for damage signatures such as heat warping, torn skin, rivet patterns, and recognizable structural edges. This comparison helped distinguish areas that had clearly burned from areas that had been cut away or gone missing later. But the result could not turn every absence into a conclusive looting entry. If a component was visible in a wartime photograph and absent in the modern crates, the safest conclusion was only that it disappeared sometime after that photograph, unless a more specific removal record existed. With the tagged pieces isolated from the field and cross-referenced against historical archives, the team faced the engineering challenge of reassembling a structure with no intact load paths. On the laboratory floor, the heavily oxidized scraps still lacked the coherent geometry required for standard visual identification. Single pieces of twisted aluminum carried little diagnostic value, and extreme heat and corrosion had stripped away the original factory stamps. A standard aircraft restoration approach attempts to bolt or rivet adjacent parts together. This method was physically impossible for this specific case. The connecting structural nodes were entirely melted or missing, eliminating any physical attachment points. Forcing the brittle, compromised metal to hold weight would induce immediate structural failure. The forensic team had to verify the identity of the highly degraded pieces using an entirely different operational logic. To solve this spatial problem, the investigators executed a rigorous process of grid reconstruction. The team drafted an extensive scaled dimensional matrix directly onto the flat, controlled surface of the museum floor. They began transferring the physically tagged scraps from the transport crates into this horizontal mapping zone. The operational rule was strict spatial isolation. Instead of attempting to force physical connections between the heat-weakened parts, the analysts manipulated their relative spacing within the grid. They utilized original manufacturer blueprints to establish the required mathematical distance between known major components, such as a surviving wing spar section and the forward firewall alignment. With the recognizable anchor pieces locked into their exact scaled coordinates on the floor, the empty void between them became a quantifiable structural zone. The analysts then evaluated the hundreds of unidentifiable scraps. For an otherwise unrecognizable bracket, the grid spacing dictated the aerodynamic and mechanical volume available in 3 dimensions, projected down onto the flat floor. The grid effectively simulated the missing structural load paths mathematically. If the drawings and the reference aircraft showed that a fragment's size, curvature, fastener pattern, and position were consistent with only a small set of locations, the team could assign it with higher confidence. The physical metal no longer had to support its own weight or match an adjacent seam to contribute to identification. The team used proximity, aircraft drawings, and the reference A6M2 together rather than relying on spatial default alone. The field tags were vital during this phase because they preserved the record of where each larger fragment had been documented before removal. As individual fragments were shifted across the grid to test different structural hypotheses, the tags ensured that the analysts maintained a perfect forensic record of each piece's material origin point. The spatial reconstruction relied on geometric deduction, reverse engineering the fragmented remains by mapping the empty space around them rather than forcing the surviving material into physical contact. That method translated a pile of scrap into a verified layout and allowed identification to proceed despite the material degradation that blocked standard visual confirmation. The analysts positively identified 95% of the recovered fragments, leaving a final curatorial decision on how to present a heavily destroyed, relocated airframe to the public. The museum faced a choice between fabricating a visually complete aircraft and displaying the wreckage as a damaged artifact, and it chose to present the recovered fragments in a diorama at the Pearl Harbor Aviation Museum rather than rebuild a complete airframe. A full structural restoration would have required modern material to dominate the visual result, and could have hidden the burn damage, cutting marks, and missing mass that made the artifact historically valuable. Before the verified fragments could be prepared for public display, they required material stabilization and preventive conservation. Aircraft aluminum that spent decades in Hawaiian soil and salt air could retain active corrosion products driven by moisture, salts, organic material, and fluctuating temperature. Conservation treatment can slow that process through careful cleaning, stabilization, corrosion inhibitors when appropriate, protective barriers, and humidity management. But no treatment completely neutralizes oxidation forever. The practical goal is to reduce continuing loss and keep the display environment stable enough to limit future corrosion. The physical presentation still required a display solution that avoided new mechanical damage, because the burned, cut, and missing structural nodes left the remaining aluminum unable to carry airframe loads. The exhibit therefore did not need to prove its truth by standing on landing gear or carrying historical loads. Its strength came from a ground diorama that evoked the Niihau site before the 2006 Salvage. The presentation made the missing mass part of the evidence: wing skin, tail material, engine remains, burned structure, cut edges, and empty spaces all carrying part of the story. The modern exhibit context supports interpretation, but the narrative should not describe an undocumented suspended steel subframe or a three-dimensional exploded aircraft unless installation records confirm it. Observers are not asked to imagine a complete restored Zero. They are shown the record of an aircraft shaped by forced landing, intentional fire, wartime inspection, post-war disturbance, and decades of exposure. By refusing to rebuild the machine as if it had survived whole, the museum preserved the evidentiary value of the wreckage.